Happy Monday, all. I am not at school, obviously, but you are in the more than capable hands of one of my favoriteest of favorite students from before. So let's do this. Yeah? You'll have a lot of work time today. Notes are pretty quick, and then you can get your homework all caught up. I believe one of the classes on Thursday of last week called it a catch-up day. So let's do that today. So a couple of quick notes here. First, in the retrieval, we're talking about simplifying radicals today a little bit and just refreshing your memory on simplifying radicals. Two different ways of thinking about this. So the first way that you can think about this is you can think about your list of perfect squares. 1 is a perfect square. 4 is a perfect square. 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, 225. Those are your first 15 perfect squares. Okay? So you can think about that by you can say, okay, well, 50 here is the square root of 25 times the square root of 2. Because 25 is on our list of perfect squares. So now, therefore, 25, then the square root of 25 would be 1, 2, 3, 4, 5. So then this would become an outside 5. 2 is not on my list, so that's not a perfect square. So it stays inside. So the radical here, or the simplified radical expression, would be 5 square roots of 2. So that is one way of thinking of how to simplify radicals. But you got to know your list of perfect squares. The other way that you can do this is you can say, well, 32 is 2 times 16. 16 is 2 times 8. 8 is 2 times 4. And 4 is 2 times 2. So 32 would actually be 2 times 2 times 2 times 2 times 2. And then you look for pairs. So here is a pair. That one becomes outside then. Here is a pair. That one goes to the outside then. This one is not a pair, so it stays inside the radical. 2 times 2 is 4, so the square root of 32 would be 4 square roots of 2. Ms. Federici is now going to pause the video so that you and give you 2 minutes to do the other 4 here in the retrieval. Square root of 20 would be the square root of 4 times the square root of 5, so it would be 2 square roots of 5. Square root of 27 would be the square root of 9 times the square root of 3, which would be 3 square roots of 3. 72 is 2 times 36. 36 is 4 times 9. 4, is 2 times 2. 9 is 3 times 3. So 72 is 2 times 2 times 2 times 3 times 3. Here's one pair. Here's one pair. Actually, I'll move that arrow over a little bit. And this one is not a pair. So then this would be 6 square roots of 2. $48 is 8 times 6. 8 is 2 times 4. 6 is 2 times 3. 4 is 2 times 2. So 48 is 2 times 2 times 2 times 2 times 3. There's a pair. There's a pair. Not a pair. Doesn't get out. So 2 times 2 is 4. So this is 4 square roots of 3. Good stuff. Okay? What I would like you to do now is I'll give you about 4 minutes. Well, actually, we'll call it 5 minutes. Ms. Federici will pause the video again. We'll have 5 minutes here to do these 4. Are they arithmetic or are they geometric? And what is their explicit equation problems? And we're back. In this first one, in part A, it appears to me like we are multiplying by 3 to get to the next term, which would make this then be a geometric, and its equation would be f of n is equal to 4 times 3 to the n minus 1 power. In part B, it appears that we are adding 8. So that makes this one be an arithmetic. My explicit equation would be f of n equals 4 plus 8 times n minus 1. But we want to make that be nice and neat. We want to expand our mathematical knowledge. So that's going to be 4 plus 8n minus 8, which is going to be 8n minus 4. In part C, it appears that we are dividing by 4, which is the same as multiplying by 1/4. So since we are multiplying, that is geometric. And my function would be 160 times 1/4 to the n minus 1 power. In part D, we are adding 20 each time. That makes this one be arithmetic. So we would have f of n equals 20 plus 20 times n minus 1, which is going to be 20 plus 20n minus 20. So f of n here is just 20n. Much cleaner if we do math in our equations. Good stuff. Oops, went too far. Okay. Simplifying each expression using exponent rules. Again, let's pause here, Ms. Federici, and let's give them some time to work on this one. I would think 3-4 minutes should be enough to do all of these, and then we'll come back and we'll explain what those all are. Here in this first one, I've got 5 y's at the first part. I got 2 more y's at the second part. So that gives me 7 total y's. So that one is y to the 7th power. When we have a power with a base with a power and we multiply it by that same base, then what we can just do is we can just add the exponents on that one. When we are dividing same bases with powers, then we are going to subtract exponents, top minus bottom, always. So this would be w cubed. When we have a power to a power, then we multiply the exponents. 2 times 4 is 8, so this would be x to the 8th power. D is just like letter A, so we add the exponents, so this would be x to the 22nd power. In E, we do a combination of B. So first I'm looking at p's here, and I would say to myself, which top or bottom has more p's, and the top has 2 more p's. Then I would look at the q's. The top has 3 more q's on it. The top also has the 13 on it. So this is going to simplify to 13p squared q cubed. When we have a fraction to a power, first off, that y has a 1 for an exponent. We would multiply the exponents, but we would multiply the exponents by this 3 on both top and bottom. So then this would become x to the 6th over y cubed. When we have 2 numbers out in front, we can just multiply those coefficients together. That would get me 10. Then h here has a 1 for an exponent. And so now it's like letter A and letter D, and I add those exponents. So this would be h to the 25th power. When we have coefficient numbers in a fraction, we do that part first. 10 divided by 2 is 5. And there are 22 more m's on the top than there are on the bottom. When we have a power to a power with numbers also, or with multiple things in it, that power has to go into the 3 term, and then that power has to go into the k term also. So this would be like 3 to the 4th power, k to the 80th power. 3 to the 4th power is 3 times 3 times 3 times 3. which is 81. So this is 81k to the 80th power. In terms of letter J here, in terms of the numbers, 24 divided by 3 is 8. The h's cancel each other out because I've got one h on top and I've got one h on the bottom, so those just cancel each other out. And the g's, there's 7 more g's on the bottom, so I would leave those 7 g's on the bottom. So it's g to the 7th on the bottom. In k, this exponent of 4 needs to go into the m. It also needs to go into the n. So this would be m to the 12th power over n to the 40th power. In letter L, we have a P, and then we have 7 W's. So it's W to the 7th power. Once again, let's give them, Ms. Federici, let's give them some time here to do this one, complete the table, graph the function, and then state the domain. For all of these in this table, I'm going to put those x values in place of x, and then I'm going to do the math. So negative 2 times negative 3 is positive 6. Positive 6 plus 6 is positive 12. Negative 2 times negative 2 is positive 4, plus 6 is positive 10. Negative 1 times negative 2 is positive 2, plus 6 is 8. Negative 2 times 0 is 0, plus 6 is 6. Negative 2 times 1 is negative 2, plus 6 is 4. Negative 2 times 2 is negative 4, plus 6 is 2. Negative 2 times 3 is negative 6, plus 6 is 0. Going over and graphing them, I think this is a 10. 2, 4, 6, 8, nope, it's a 9 by. Okay, so negative 2 would be at 10, which would be right there. Negative 1 would be at 8, 6, 4. Oops, now why am I off? Oh, I went off by 1 up there. That's why. Sometimes you make a little mistake. Miss Federici knows all about that. I've made many mistakes when she was my student. Okay? So it makes a line. Okay? So if we go off of the... Oops, I should put my line in here first. If we connect our line all the way across our graph, we get this. If we talk about domain, we can talk about domain in 2 different things. If we're going from the table, then our domain would be negative 3 is less than or equal to x is less than or equal to positive 3. If we're going from the equation of the line, which we graphed and we connected and we went on forever and ever and ever, then our domain is all real numbers because there is not a number that I can't put in to that function, that continuous function. Make this be a little bit better. There we go. Hook it in there a little bit. Okay? Love it. Give you a couple of minutes. Again, we'll pause the video here. Give a couple of minutes to do this particular problem. So his time is decreasing by 2.5%. So that's going to be 100% minus 2.5% is going to be 97.5%, which means my R value then would be 0.975 when we go to the equation. So the equation is going to be f of t, because we're talking time here, so let's switch it over to t, is going to be 19 times 0.975 to the t minus 1 power. If you used n, that is totally fine. Totally fine. Okay? This would be a discrete situation because you can't run 2.5 races, if you will. Okay? Then we're looking for the time in our 15th race. So that's going to be 19 times 0.975 to the 15 minus 1 power. I get, when I type that in my calculator, 13.3296. But it also said we are rounding to the nearest minute. So therefore, I would say that this would be 13 minutes there. And the domain would be the natural numbers because he wouldn't have a time for race 0. So we don't need to include 0 in this one. With that being said, your homework tonight now, and you have the rest of the time to work on your homework. Your homework is the Ready, Set, Goes from this section, and will be due tomorrow when I am back. Thanks for playing along.